Welcome to homework.
Okay, we need to find the wavelength in nanometers of the bright line of the hydrogen emission spectrum following the n equals 4 to n equals 2 transmission. All right, so n1 equals 4 and n2 equals 2, which, as you can imagine, if we consider the Bohr model for a second, looks something like that. Okay, and we're trying to find the wavelength of that photon. Okay, well, let's recall that the energy of a transition is equal to z squared, where z is the charge, right? M, where m is the mass of an electron, e cubed, e to the fourth power, where e is the charge of an electron, times 8 times h squared, that's Planck's constant, times the permittivity of space squared, times 1 over n1 squared minus 1 over n2 squared. All right. Now, what we want is not necessarily the energy, right? What we want is the wavelength. Now, energy is related to wavelength through the following equation, right? So energy equals h, which is Planck's constant, times c, which is the speed of light, over wavelength, which implies that wavelength is equal to Planck's constant times the speed of light over the energy, right? So basically, we need to find 1 over this energy times Planck's constant times c. We can also sort of simplify this equation in a way that hopefully this makes sense. So let's say for a moment that we consider, instead of solving for the wavelength, solving for 1 over the wavelength, in which case we'll get that it is equal to E over hc, which would be equal then to z squared m e to the fourth over 8 h squared epsilon naught squared 1 over n1 squared minus 1 over n2 squared, all over hc. Okay. Now, if we consider just the mass, like these terms right here, those can all be combined into what is known as the Rydberg constant, RH. Okay. And then that would be times c squared, and then we can put in 1 over n1 squared minus 1 over n2 squared. Okay. So we get that 1 over the wavelength is equal to the Rydberg constant times the charge squared, which for hydrogen is just 1. So we can actually ignore that entirely. Okay. It's getting a little simpler. Put that back on accident. Okay. So now we're at 1 over the wavelength equals the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. Okay. And we have that the Rydberg constant for hydrogen equals 1.097 times 10 to the 7th, and this is meters inverse. Okay. So basically, we can get 1 over the wavelength equals something over meters, and then go from there. So let's plug in what we know. We know 1.097 times 10 to the 7th meters inverse. And then we've got 1 over n1 squared, which we said was 4 is n1, so squared is 16, minus 1 over n2 squared. N2 was 2, so that's going to be 1 over 4. Okay. And we can just take the difference between these. Remember that 1/4 is the same as 4/16. Okay. So we're going to get, in fact, it's going to be a negative number, but if we swap the delta E, right, we can basically swap the sign on this. So consider instead, basically just treat this as 3/16 for the time being. The negative sign is unimportant. We should have fixed it up here when we were using delta E for absorption, but we wanted to do emission instead. Yeah. Yes. Okay. So we get 1.097 times 10 to the 7th meters inverse times 3/16. I'll put this into a calculator. And I get 2.057 times 10 to the 7th meters inverse. That's 1 over lambda. So that if I take the inverse of both sides, so I get lambda equals 1 over 2.057 times 10 to the 7th meters inverse. We get 4.862 times 10 to the negative 7th meters. And in nanometers, if we want to convert this to nanometers, we say there are 10 to the 9th nanometers in 1 meter. And we get 486.2 nanometers.